Systems of linear equations in three variables. This video will help you verify the solution of a system of linear equations in three variables and solve systems of linear equations in three variables. Systems of linear equations in three variables and their solutions. In general, any equation of the form ax plus by plus cz equals d, where a, b, c, and d are real numbers that are not equal to 0, we get a system of linear equations, three of these things, with three variables. A solution of the system is very similar to what we had with a solution of a system of two equations and two variables. There we got an ordered pair. Here, since we have three variables, we're going to get an ordered triple. So that's what we're looking for when we're solving a system of three equations with three unknowns, is this ordered triple. Let's take a look now at an example that will show you how to verify if an ordered triple is in fact a solution to a system of three linear equations. So let's take a look. We've got this system, three equations, three unknowns. Notice we've got an unknown x, y, and a z. In order to solve for three unknowns, we'll need three equations to do that. And so we have three equations here. And all we're trying to do now is just see if this ordered triple is going to be a solution. So just like an ordered pair, we had x and y. Now we're going to add this third dimension to that, which is z. All right. Now, when we had x and y in an equation, that represented a line. If I had, an equation with x, y, and an equation equal to some number, that was a line. Now, if we add a third dimension to that, x, y, and z, now we have a plane. So remember, a plane is no longer a line. It's in fact a two-dimensional shape here. So these three things represent planes here. And what we're doing is we're looking for the intersection of these planes. And if they intersect at this point, -1, -4, +5, then we'll consider this point a solution to this system of three equations. And verifying that is really easy. All we're going to do is we're going to plug these values in to each of the equations and make sure we end up with a true statement. So you can see me here taking the first equation and plugging my x, y, and z in there, and notice I end up down here with a true statement. So I'd say, all right, that works in equation 1. Now I'm going to check that in equation 2, and sure enough, I end up with a true statement down there. Check it in equation 3. Sure enough, we end up with a true statement down there. So we would want to say at the end of this, I'm not done quite here yet. I've kind of just verified that these are all work in the equations. So I would say, yes, -1, -4, +5 is a solution to the system. All right, I think this is going to be a pretty straightforward process, plugging the values in and seeing if it works. Just make sure you include this statement. If it does work, if they don't work in one of them, then you would say, no, this ordered triple is not a solution. So just make sure you include that on your answers. But I think this is pretty straightforward, so we're not going to do a practice on that one. So now let's take a look at solving a system. So now we're going to be given this set of three equations with three unknowns in there, and we want to solve it. And the way that we solve it is really similar to the way that we solved when we had two equations and two unknowns. So what we want to do is we want to start with this three equations, three unknowns, and kind of reduce it back down to two equations, two unknowns. Once we get there, we'll be doing the exact same thing we did before, solving two equations, two unknowns. So we reduce the system to two equations with the same two variables in them. And so the way we usually accomplish this is by taking two different pairs in our system of three equations. We take two different pairs and eliminate the same variable from both pairs of equations. When we eliminate both pairs, same variable in both pairs of equations, then we end up with a system of two equations, two unknowns, and then we solve using the same techniques we had before, either elimination or substitution. Once we get an answer to the two equations, we get two of our variables found, then all we have to do is take those two variables, substitute it back into any one of the original equations with three variables in it to solve for the third variable, and then that will give us our ordered triple. Once we have our ordered triple, then we go ahead and we check to make sure that works. All right, let's take a look at an example now to see how this stuff in process. So we've got our system of 3 equations, 3 unknowns here. We want to solve it. So what we're going to do is we want to look for combining 2 pairs here to eliminate the same variable. And it looks like, as we're setting up here, if I look down at my x's, I could definitely eliminate those. X, I could manipulate those to eliminate an x. Y would be a little trickier, but notice z, boy, z looks like the easiest one. So this is what we want to do every time we solve one of these systems. You look at the variable that's going to be the easiest to eliminate. So what we're going to do now is we're going to combine these equations to eliminate z. So it looks like these two, I could combine them as is, and then maybe combine 1 and equation 3 there. So let's label these two. That helps a lot. So I'll call this equation 1, equation 2, equation 3. So it looks like we're going to combine 1 and 2 as is, and then I'll combine 1 and 3, but I'm going to multiply 1 by positive 2. Because if I multiply this whole equation by 2, then I'll have negative 2z plus 2z, and I'll be able to eliminate the z there. So let's come down here and take a look at that. So here I am combining 1 and 2, and just combining those as is. So adding these guys up, x plus 3x is 4x, 4y plus 2y is 6y. The z's are gone, that's why I'm doing this. And then 20 plus 8 gives me 28. So now notice I'm down to a system of 2 equations. Sorry, I just have 2 variables in there, x and y. Now I'm going to combine 1 and 3, but I'm multiplying 1 by 2, as we discussed. So here I am multiplying first equation by 2. Now once I do that, now I'm ready to add to drop out these z's. So add these guys up, I get 4x plus 5y equals 24. And so now I'm home free, because notice what I have now is a system of 2 equations, 2 unknowns, both x's and y's. We already know how to solve this. So all we're going to do is use the skills we've already learned to solve the equation here for x or y, and then use substitution to get the other variable. So let's take a look at that now. Okay, so I'm going to eliminate, looks like I'm going to eliminate the x's here. Notice they're pretty well set up. I just multiply the bottom equation by a negative. Once I multiply by a negative, now I combine them. My x's drop out. I'm left with y is equal to 4. Once I have y is equal to 4, I'm going to substitute that back into one of my original equations. I can put this y back into this one or this one, but we're still just right at this point just focusing on the 2 equations, 2 unknowns, not back up into our system of 3 equations yet. So I substitute into either one of those. Looks like here I picked the top one to substitute in, so I'm taking this equation here, substituting 4 back in there for y. You can see me plugging that in right there. Go ahead and solve this thing, and then we get x is equal to 1. Now all I have to do is take this x and y, plug it back into one of my original equations with 3 unknowns in it, and we'll find out what z is. Alright, so it looks like I substitute this back into one of the original equations. Looks like the first equation, looks like I picked equation 1 there. I put x and y in there, and you can see once I put x and y in there, it's now easy to solve for z. And so I find that z is equal to negative 3. So here is my ordered triple as the solution. Now one thing that happens as we're solving this system of 3 equations and 3 unknowns is if we make any tiny little mistake in there, it will mess the whole thing up. So you want to make darn sure you check your answers here, because it's so easy to make a small sign error or something like that and your answer won't work. So every time you solve a system of 3 equations, we want to go ahead and quick plug it back in and make sure it works in all 3 of the original equations. So here I am checking to see if this thing is a solution. I check in equation 1 and it works. Equation 2, it works. Equation 3, and it works. And so after I've done that now I can say, all right, here's the solution set to my system of 3 equations and 3 unknowns. I get the ordered triple. X is equal to 1, y is 4, and z is negative 3. All right, now we're going to take a look at a practice problem. And you'll notice I've given you the steps here that we just followed in that example. So use these steps to solve the system. Now one thing that I want to make sure that we're going to do, because there's lots of different ways we could solve this system. And just to be consistent so that when I work it back for you, let's look here. Let's look down at our x's, see if it's easy to eliminate x, y, or z. I think there's a good case for either eliminating an x here to start off with or a z. But just to make sure we're all on the same page and we're doing the problem the same way, let's go ahead and let's eliminate those x's first. So eliminate the x's, we'll be left with a y and a z. That will be our system of two equations, then solve those. If we kind of follow that path together, our problems will look similar when we look at the answers. Okay, go ahead and pause your video player now and answer this practice question. When you're done, hit play to see how you did. All right, as discussed, we're going to try to eliminate x here. So let's see, here we got equation 1, 2, 3. So it looks like I'm going to combine 1 and 2, but I'm going to multiply the bottom equation times 2. So I'm going to take equation 2 and multiply by 2 so I can drop the x's out here. So let's see, I'll write the top equation as is. 2x plus 3y plus 2z is equal to 3. Is equal to 3. I'm multiplying this bottom equation by 2, so negative 2x plus 4y minus 2z is equal to 4. All right, now make sure you multiply this 2 times our constant on the other side there. That's an easy place to make a mistake, so make sure we do that. All right, I'm going to add those two guys together. As discussed, the x's are going to drop out. I'm going to be left with 7y. Hey, look, the z's drop out nicely for me too. That's great. So the z's are gone as well. So I'm just left with this statement. 7y is equal to 7. All right, let's combine now. At this point, I guess we could just solve for y. We know that y is equal to 1. Before we can do anything with that, though, we'll have to solve, make our other combination here to drop the x's out as well. So I'm going to combine these two guys, equations 2 and 3 as is. So we're adding those guys together as they are. X's drop out. I get y, and then negative z minus 2z would be negative 3z is equal to 2 negative 4, so negative 2. So now, since we got y solved for, I'm going to plug y right over into there. So I'd have this statement 1 minus 3z is equal to negative 2. All right, subtract 1 from each side. Negative 3z is equal to negative 3. So it looks like z is also going to be equal to 1. All right, once I solve for both y and z, now I can plug these values into any of these equations above. And honestly, if I look here, equations 1, 2, or 3, those are all pretty simple, pretty small numbers to work with. So I don't think it's going to make much of a difference which one I choose. I'll choose equation 1 since I haven't marked on it there. I don't have any markings or multiplication symbols. So let's see. I'll have 2x plus 3 times 1, substituting for y, plus 2 times 1 is equal to 3. Is equal to 3. All right, let's see. So 2x plus 3 plus 2 is equal to 3. So it looks like this is 5, so I'll subtract 5 from both sides. And I'll get 2x is equal to negative 2. And then x is equal to negative 1. Okay, so here's my proposed ordered triple now. I've got negative 1, 1, 1. Hey, easy numbers to check. Okay, now I want to go back through and check all of these. Now, I'm going to erase this because I need to save some room, but on your piece of paper, you'll want to leave this because you want to leave all your work here, because if we make a mistake, you're going to want to go back and try to figure out where you made a sign error or a multiplication error, some small error or something like that. So I'm going to leave my answer. I'm going to erase this, but you should on your paper not erase it because we want to go find the mistake if something didn't work out here. Okay, I've substituted them all back in now, so we're checking this point, negative 1, 1, 1. All right, let's check in equation 1 here. This is equation 1 right there. So let's see, 2 times negative 1 is negative 2, plus 3 plus 2 is supposed to be equal to 3. So let's see, negative 2 plus 3 would give me 1, 1 plus 2. Hey, checks, perfect. All right, let's go now to equation 2. Now I'm going to have the opposite of negative 1. Notice I'm putting a negative 1 in there for x, so I have the opposite of negative 1, so it's going to be positive 1 plus 2 minus 1 equals 2. Well, sure enough, if I take 1, add it to 2, and then subtract 1, it's going to give me 2, so that checks. All right, let's check this last one here, equation 3. So I have negative 1 minus 1, that's going to be negative 2. Negative 2 times 1 is also negative 2. Well, negative 2 plus negative 2 is going to give me negative 4, and that checks. So I would say the ordered triple is a solution to the system. Okay, now let's talk about some situations that can come up. We already talked about in 2 dimensions then, when we were solving a system of 2 equations, how we ended up with a single answer, consistent system with a single answer, how we ended up with a consistent system with an infinite number of solutions, and also we would end up with a system where we'd have no solutions. Well, very similarly, we're going to have 3 different cases here, all right? And so this is the case we just solved for here. We solve the system, and it has a single solution, which is after we do the elimination and solve the thing, we end up with this single ordered triple. And here's kind of a graphical picture of what's going on here. When we have this system of 3 unknowns now, we're no longer getting a line, we're getting a plane. So each of these equations here that we looked at was representing one of these different planes. And so all of these planes, if they intersect in a single point right there like that, then we end up with this ordered triple. So that is one possibility. So this is kind of a picture of one solution. All right, a system now that has infinite number of solutions is when we're going to solve it, and all the variables drop out, and we're left with a true statement, which is exactly the same thing that happened to us when we were solving a system of 2 equations. So that's really convenient. We end up with this true statement after the variables drop out, where we get some true statement like 0 equals 0 or 10 equals 10 or something like that. Well, if that situation arises, then what's happening is these planes are intersecting now no longer in a point, but they're intersecting in a line. So this is what infinite solutions looks like. We've got the 3 planes coming together, the green one, the orange one, and the blue one, except instead of intersecting in a point, they are intersecting in this line. And so since we get this line, which is traveling infinitely in both directions, that's how we end up with an infinite number of solutions. It doesn't mean that every single point combination we come up with is a solution. All it means is that these solutions are going to end up on this line, and on that line there's an infinite number of solutions. Okay, last case scenario, just like before, is a system that has no solution. And so exactly the same way when we solved a system of 2 equations, 2 unknowns, we're going to work the solution out. Well, all the variables drop out in the process, but now instead of a true statement, we're left with an untrue statement, like 3 equals 0. Then we have an inconsistent system, meaning there's no solution here because they don't cross. And so that can happen kind of in 3 different ways. You know, the planes could intersect, so this would be no solution. All 3 of these would be no solution. The planes can intersect, but their points of intersection are separate. So notice the planes intersect each other here, here, and here, but they don't all intersect each other at the same time. And that's the same situation with this one. The planes intersect, but they don't come together all at the same time, or the planes never intersect each other at all. They're all kind of parallel planes, and they don't have anything in common between any of the planes. So that would be a no solution case, and again, that's when we're solving the equation, variables drop out, we're left with an untrue statement. And I'd like to give a little shout out to Lumen College Algebra for providing these sweet plane images to help us understand how these planes intersect, or the possible cases that come up when the planes intersect.